Hollywood loves to write about alien life for both the big and the small screen. They offer a wide variety of diversity as to the nature of life forms. In reality, finding life outside of Earth has proven elusive. In spite of looking, we've not found any evidence of life anywhere outside of Earth, including elsewhere in our own solar system. Life as we know it is based on carbon and water. What is it about carbon that makes it so special? Are there other atoms that can become the backbone of life? Next, we'll talk about what makes carbon such an important part of life and what other atoms, if any, can provide the same life chemistry. Stay tuned. Life on Earth is based on carbon chemistry. From the simplest life forms to the most complex, all are built on carbon. But why carbon? We need to consider three things: abundance, stability, and complexity. First, we'll talk about abundance. When answering why carbon, interestingly, carbon is not the most common element on Earth. Oxygen gets that distinction. And it's not the most common in the universe. Hydrogen and helium are by far the most abundant. Carbon is not the most abundant element in the solar system either. Carbon is not even the most abundant element in our bodies, making up only about 20%. But it is found everywhere in our cells, including the most important molecules in our bodies, those essential to biological processes. When we compare the abundance of the most common elements of both life and the solar system, we see a strong correlation, especially with carbon. This doesn't seem like an accident. But what else is there about carbon that makes it so effective of a choice for life? Next, we'll talk about complexity. It turns out carbon is not the most stable atom. That distinction belongs to the noble gases on the right. The most stable atoms are those that have full outer shells, the valence shell. This represents the lowest energy state. Atoms seek the lowest energy state, so they try to chemically react with other atoms to fill their outer shells. Nature is always seeking out low energy states. Atoms that have full outer shells generally do not chemically react to other elements to fill their already full outer shells. They are chemically inert. Hydrogen has only one electron in its outer shell. Helium has two. Helium is a stable atom, whereas hydrogen wants to bond with other elements to have a complete outer shell. Argon and neon both have full outer shells, while chlorine has a vacancy. Oxygen has only 6 valence electrons, so it wants to combine and gain 2 extra electrons. We see this happen when oxygen combines with hydrogen to form water. The maximum number of bonds that an element can have is illustrated by its column in the periodic table, starting with a maximum of 1 bond in the column on the left. It increases by 1 bond until we get to carbon. Carbon is capable of forming a maximum of 4 bonds. As we move further rightward, the number of bonds goes back down to 0 in the noble gas column occupied by helium. Carbon, therefore, is in the column allowing the maximum number of bonds. Carbon has 4 valence electrons, so its low energy state occurs when 4 additional electrons are filling its outer shell. It can share up to 4 electrons from other atoms to make it more stable. This makes carbon very versatile. Carbon is known as a promiscuous atom. It can easily form bonds with a variety of elements, including other carbon atoms to make long chains of complex molecules, including those necessary for life. Here we see a fatty acid molecule where carbon bonds with other carbon, hydrogen, and oxygen. Carbon, therefore, is uniquely able to take part in an incredible number of chemical processes. This includes the long, stable chains of molecules that carry information, like DNA. DNA carries all of the information that makes up living things. Carbon is the backbone of complex molecules like DNA because it is uniquely able to handle the necessary complexity. But what about other elements, like oxygen? It can carry only 2 bonds, so it can't form the complex molecules, like carbon can. What about boron? It can form 3 bonds, so it supports more complexity than oxygen. The problem? Boron is very rare, too rare to be used to support the needs for life. And what about silicon, or nitrogen? Silicon is in the same column as carbon, so it too can bond with up to 4 atoms. In fact, everywhere you have a molecule with carbon, you can substitute with silicon. And silicon is very common, even if it is locked up in rocks. So to return to our question, we'll need to consider our last requirement, stability. We need a strong foundation upon which to build the scaffolding for life's critical molecules. Silicon's covalent electrons are on the 3rd shell, farther from the nucleus than for carbon's. That means that silicon's electrons are more weakly bound to its nucleus. As a consequence, the bonds silicon makes are weaker and thus less stable. The carbon-carbon bond strength is about 1.5 that of silicon. Nitrogen's bond strength is about half that of carbon. This strength gives carbon a superior backbone, while allowing other parts of the molecule to chemically bond with other molecules. An additional drawback for silicon affects an organism's necessary ability to produce energy for cells by respiration. In respiration, an organism takes in oxygens as a mean to break down glucose to produce energy. As a result, the waste product of CO2 is produced. In this process, carbon is bonded with oxygen to create CO2, a gas which is easily expelled. When silicon is bonded to oxygen, it forms silicon dioxide, or sand, a solid. This would create a unique biological challenge for any silicon-based organism. Now for a striking visual. Looking again at the periodic table, let's eliminate the atoms that are not realistic for the backbone of life. First, we'll eliminate all but the first 3 rows, the rows containing the bulk elements, or building blocks of life. Next, we'll eliminate the inert atoms. We can also eliminate the atoms that can't form more than 2 bonds. Now, remove all exceedingly rare elements. Lastly, we should remove from consideration those remaining that do not have strong bond strength. We're left with only carbon. Carbon is the best choice for life because it is the best combination of abundance, ability to form complex structure, and have stable bonds with other carbon atoms. That doesn't preclude life from other elements. Life based on germanium or tin could happen. However, those heavier elements are far less common. Germanium is 5 orders of magnitude less common than carbon. Bond strength generally goes down with increasing atomic size. As a result, heavier atoms will form potentially more unstable molecules. They may be more likely to break down as the environmental conditions on a planet or moon change dramatically, with day-night, seasonal, or even longer-term rhythms. As a result, more extreme environmental variations, common on planetary systems and moons, may become hostile to life. Remember, some planetary systems experience dramatic changes in climate in very short time periods. There's also a strong connection between carbon and water. All life as we know it relies on water as a solvent. Water is known as a universal solvent, meaning that many substances easily dissolve into it. All life needs to take in nutrients to generate energy. It also needs to remove waste. Water is ideal for both tasks. It just so happens that temperatures and pressures on Earth are such that water can exist in 3 forms: solid, as ice, liquid as water, and gas as vapor or clouds. And it does so in a very tight range of temperatures on Earth. Temperatures that are hospitable to stability of the large molecules of life and allow rapid chemical transport needed for biological processes. If temperatures are too cold, water turns to ice and chemical transport slows dramatically. However, Water has a unique property in that its solid form is less dense than its liquid form. Therefore, ice can provide a barrier between the warm subsurface water and the harsh space environment so that life can exist in between. If water gets too hot, the carbon molecular chains will break too easily, along with the information that they carry that are necessary for life. The three phases of water help distribute water everywhere on Earth, anywhere that life can expand into as conditions warrant. Other chemicals, like ammonia or methane, are similarly effective solvents, like this artist's conception of the three forms of methane on Saturn's moon Titan. However, methane is not liquid except at very extreme temperatures that will be hostile to carbon-based life. Life based on carbon provides a unique set of stability, strength, and abundance to enable the organic chemistry needed by life. Coupled with water, we have the chemistry we need for life's chemical processes. We can't rule out life based upon other combination of atoms, but that life might have even more challenges to overcome than carbon-based life. Lots of questions still remain when considering the possibility of intelligent life in the universe and whether they can come here. Will life even develop and be multicellular? And if so, can it develop to intelligence? Will the intelligent life live on a planet with a transparent atmosphere to enable it to study the universe and understand its place in it? Or will it live underwater and not be able to travel to planets beyond its water environment? Finally, will the intelligent beings based on less stable atoms live long enough to develop science to investigate its place in the universe? We finally ask the question, are these even the right questions? Only time will tell.
I don't think he's from around here.
Pepsi, the choice of a new generation.
There's only one thing we could do, kid. You gotta go up to them. Him.
Are you sure?
Don't worry, there's no sugar. All right, hey, bring me that. Go get him, kid.